Okay, so we'll talk about virtual memory. Virtual memory is used by operating systems so that, for example, if you had a program that was too big to fit into the main memory of your computer, we could still run the program just by putting in parts of the program, the part that happens to have the instructions we're running at the moment. So here's a definition from Wikipedia of what virtual memory is. And the general idea is that one of the things we have to do when translating where an address in your program is, where it is located in the main memory at the moment, we're going to do a translation very similar to this. So this is something we might be easier to follow if you were to write a book. If you wanted to write a book, you'd write a manuscript. And since we're computer scientists, we always start on page 0 or number 0 when we start counting. So for example, if you were to write a book that had, a couple hundred lines to it, gave it to a publisher, and the publisher decided to print the book where each page had 32 lines on it, then if you wanted to find, for example, line 135, which would really be the 136th line because you started at line 0. So when you got to the one number 135, if you asked yourself, where is this line? And your book was published in a book that has 32 lines per page, we'd have to do a computation where first we find what page it's on, and then once we find what page it's on, we'd then look at what line within that page we're on. So how would we do that computation? We would take the line number, 135, and divide it by the page size, which we're saying in this example is 32 lines. And then whatever that comes out to, we would round that down to the nearest integer. And that would tell us we are on page number 4, which is really going to be the 5th page, because we start on page 0. So page number 4 is actually the 5th page in the book. Okay, and then the question is where on that page. So the first step is we found the page we're on. The second step is now that we're on that page, how many lines down is it? And we would once again take 135, our line number, and do a modulo, divide it by 32, and then see what the remainder is. And in that case, the remainder would be 7, so we would be line number 7, but the lines start at 0, so it would really be the 8th line of the page number 4, which is the 5th page of the book. Okay, so we would go to page 4 and then go to line number 7, and that's how we can find that page. So we're going to do a computation very similar to that. So the idea is when you write a program and you load it onto your disk drive, your program, you could be program A, and it starts here and it just ends wherever you decided to let it end. The operating system could come along and say, I don't want to be constrained by the rule that I must load the entire program into main memory, otherwise it can't run. Because first of all, like I said, your program could be so big it can't fit in main memory, so we'll only bring in parts of it. The other thing is there might be so many programs running at the same time your program is running that the operating system just doesn't have enough room for all the programs that are running. So it'll give parts of main memory out to your program, and you can bring sections of your code, divided up into pages, into main memory, and just scatter them throughout main memory wherever they can fit, or wherever space is available at the time. So this now means the operating system has to keep a table. Somehow it has to have a table that says, oh, okay, I got page 1 of your program is over here, and then in my table I have page 3 of your program is over here. And page 4 in your program is over here. So where is page 2? Page 2 is not in memory at the moment. So if you were running code that said, you were running code along page 1 and then you went into page 2 and you try to execute code out of page 2, we would go looking for page 2 and find it's not here. So if we found it's not here, we could go out to the disk drive and bring it in and add it to this table. If the operating system constrained us to say we only have 3 places to put pages, then we're going to have to pick one of these to get rid of, and we'll talk about that next class, which one do we pick. Okay, so the idea is basically from your point of view, your program starts at line 0 and just goes until it ends. From the operating system's point of view, it's going to cut your program up into pages and bring those pages in and out of memory. So maybe showing the same exact picture, but just putting bits down. Here's an example where we have our operating system. Here's page frame 0 and 1 and 2. And the first thing when you power on your computer is the operating system loads the operating system into some of the pages. The entire operating system doesn't have to be in, just the parts that are going to be running initially need to be in. And then at a certain point, there are going to be page frames that are going to be available for application programs. So in this case, Process A's page number 1, which is really their second page, is loaded here. Process B's page 2 is loaded here. Process A's page 0 is loaded here. This happens to be an empty frame at the moment. Maybe a program had a page there and it just ended, so it happens to be free. Process A's page 4 is over here. And Process C has page 0, page 2. So it must have a table somewhere keeping track of where these are. Now at a different point in the operating system, storage, we have to have our page table. Our page table is saying that from our point of view, what we think is page 0, our program starts at 0 and just goes until it ends. So what we consider page 0 happens to be located, we have a set of bits, and I just kind of put in decimal what the values are. So it's in frame 98 is Process A's page 0. And then Process A's page 1 is located in frame 96. And Process A's page 4 is located in frame 100. And all other pages are missing at the moment. So if we were running instruction, let's say there was a while loop that started in page 1 and then ran to page 2, started executing code into page 2. There is no page 2. We'd have to go out to the disk drive, bring it in, find a place to put it. Maybe the operating system will let us use this frame. Maybe it won't. Maybe it's dedicated it to another process, and then we have only these 3 to put in. So we put the page in and update our table accordingly. Okay, so so now the idea is when we go to do this translation, when we go to do, we're looking for a particular line within our program. We're going to divide by a page size and round down. It works out very, very nicely, and then also the modular too. It would work out very, very nicely if we intentionally chose page sizes that were perfect powers of 2. So 1K, 1 meg, those are all perfect powers of 2, or 2K, or 4K, or 8K, 16 meg, 32 meg. Using perfect powers of 2 makes that math come out really, really easy. We'll get to that in 1 second. This is just a picture, a reprint of something we talked about earlier in the semester when we were talking about writing to memory. So remember we had 4 bits, W, X, Y, and Z, and we were picking one of these nibbles to write it to. So we would put a number on the MAR. The MAR would turn 1 wire on, and that would allow these 4 memory locations to take on a value. Well, just think of this as a bigger scale. Suppose this is now considered not a register, but a page. So we're taking a page that's 4 bits, and we're picking one of the 4 frames to write it to. If we wanted to make the page size bigger, let's say in this picture we wanted to make the page size 8, 1, 2, 3, 4, 5, 6, 7, 8. And then these 8 bits would be a second page. So this would be like a 2. This would be a page frame, and this would be a page frame, and we would have to have, I guess, 8 bits to write to. Would it take longer time to write 8 bits into memory as opposed to 4 bits into memory? Well, what would be the adjustment to the picture if we were going to write 8 bits all at once as opposed to 4? So I just want to get the idea that even though if we make our page sizes big, how does that affect us as far as writing the entire page over? Does it take longer to write? Would it take longer to write 2 meg of data into memory as opposed to 1 meg? or 1K? Does the amount of data being copied over take more or less time, or approximately the same amount of time? Does anyone have a guess for that, or? Right, so in this, like I say, in this case, we have 4 bits we're writing into one of 4 pages. So here our page size is 4 bits. If we converted this, like I say, the operating system can arbitrarily pick a page size. Suppose we decided to make our pages much bigger, therefore we have less of them. We made 8-bit pages. And then we'd have 8 bits over here to write over. Would it take more time? Because we're writing more data with it. Would it take more time, or would it not? It wouldn't? It might even be slightly less, because instead of putting, we'd only need 2 inputs here, right? One input, a 0 or a 1. If it's 0, it's the top page, and 1 is the bottom page. And going through the MAR would actually have less electronics. And then, since all these bits are wired in parallel, they'll all be written in the same amount of time. So having bigger pages doesn't make us take more time in writing. So, suppose we had an address. Now, the address from the point of view of us, the person who wrote the program, our address, we started our program at address 0, and we just keep writing out into our program. Where our page happens to be loaded in main memory is arbitrarily chosen at the time your program is running. But let's say we had this address, 0100000111, and the operating system decided to use a page size of 32. Now that's unusually small for a real operating system. So again, this is just to make the point. But here it would be just like the last example. We would be in page 4, which is really our 5th page, because page 0 is our first page. We would be in page 4, and then our offset, how far into that page, we would be 7 into that page. And with 5 bits, we could go from 0 down to 31. 0 to 31 for a 32-line page. So if we wanted to know where is this address loaded into our operating system, the high order bits, the 4 high order bits, tell us which page we're in, which is page 4. And the 5 low order bits tell us exactly how far into that 32-bit page we are. This works perfectly if we decided to make our page size a perfect power of 2. Then all the bits to the right of some arbitrarily decided line is the offset into the page. And all the bits over here is the actual page number. Makes the translating very easily. So there's no translation. So this part here is the modulo computation. What is the remainder after we divide by 32? Well, the last 5 bits is the remainder. So we can just copy these 5 bits down, and that's how far into the page we are. As far as the virtual page number, the page from our point of view, starting at 0, we have to then go into a table, look down the table and look for a match. We find a match. Oh, here's page 4. Where was it located? Where did it get loaded into memory right now? It got into this page number. So now we take these bits and put that in as the real page number, and then this is how far into the page we go. So that's how we do our translation, from one page to the other. From a virtual address to a real address. So does it make sense that these 5 bits is the modulo computation? We don't even have to do the computation, we just copy the bits down. If we happen to pick a page size, that's a perfect power of 2. If we didn't, then we have to take this number and actually divide it and see what the real remainder is. Okay, so the diagram for translating from a virtual address to a real address. A couple ways it could be done. One is we can take the bits that represent the page number, and we can sequentially, in software, let me go back to here, so we can sequentially say, okay, we can take the 4 bits here, and say, does it match these bits? And if the answer is no, we check, does it match these bits? No, and keep going until we find a match. That would be a software computation, and each computation is going to take time. And the question is, every time we run an instruction, do we have to go and find the real page every time, or can we somehow cut down the time of looking it up in the table? Would we have to look up in the table every time the page runs? I mean, every time an instruction runs, do we have to always check the page table to see where the page is? Or could we ever make an assumption like it's the instruction right after the current one? Therefore, we don't have to look up what page it is. Or at what point would we have to look up what page, where the page is in the table?
Virtual page is different.
Yeah, so when two consecutive instructions actually come from a different page, then we'd have to go out to the page table to look up where the page is. But if the two consecutive instructions are from the same page, we know its distance from the current instruction is the same as its distance in real memory, right? It wouldn't be somewhere else. So, every time you run an instruction, you have to remember what was the last instruction, what's the current one, and somehow quickly do a check. Are they from the same page or not? If they're from the same page, then you can just let it run. If not, if they're from different pages, we have to go out to this table and find out where it is, and then see how far it is. So how could we do that? How could we take two instructions and very quickly say, yes, they're from the same page? So just let the instruction run. Don't go out to the table to find where it is in memory. We can do that in software or hardware, right? We can say, do the high order bits of each match? Like, does A equal B? If so, don't go to the page table. If not, go to the page table. We can also do it in hardware by having two sets of bits, checking them for a perfect match, and if they perfectly match, a wire doesn't turn on, and therefore we don't have to go out to the table. So yeah, before we get into how we could do it in hardware, or hardware would be better than software, basically we have high order bits tell us the page the page number it's in, the virtual page number. The low order bits are how far into the page. We could have a page table and follow a rule that says whatever page number this is, it goes that far into the table. So in other words, we would have a table that is the size of our virtual space. And some of these table entries will be blanks because we don't have those pages in memory. So we can take the page number and add it to the beginning of the table to know exactly where the virtual page number is, and then maybe there would be an address there or maybe not. That would save time on going through the table and checking each one after another linearly in software, which would take a lot of time. So that's one way we could do it. Another way is through software, just running down the table looking for a match. And then we'll talk about a hardware way that might save us some time. But one other thing we can do is take this concept and push it to the next level. You can have a program that you could turn your program into segments. For example, like you've written code in Java where you have your code, and as your program is running, you're declaring variables that are on the stack, like int x equals 2. That gets put on the stack, so every open paren puts more variables onto a stack. Every time you hit a close paren, they get popped off a stack. You could also create class variables with a new operation, and those stay around until it has no more references to it, and then they go away. So that gets put on what they sometimes call the heap. So there are a process could have various segments to them. So you could decide to let the first batch of bits number the segment you're talking about. Then the second batch of bits is the number of pages in that segment. And the third batch of bits would be how far into that page you go. So just be taking the same concept. Your segment number, you go to a segment table, and then for each segment has its own page table. So we take the segment we're in, that tells us where the address of the page table for that segment is. And then that segment has a page table and tells us where the real address is. So operating systems do take this paging and offset into the page and then add more layers to it. And you might think this is going to cause a lot of translating, and the translating takes time. So we might want to figure out how to do this quickly. So the page translation speed becomes important. And so then, the question is, well, there's a few ways we could do the translation. Take the virtual address and figure out where is that same address in real memory. And one is through software. Software, we could do a linear search, but that would take a lot of time. We could find the real page every time we run an instruction. That would eat up a lot of time. So it would be good to bring in some hardware that helps us. And in your computer architecture class, you may have come across a piece of hardware called a exclusive NOR gate. And the exclusive NOR gate had the property, if you have two inputs on it, the output will turn on if the two inputs match. So if you put two zeros coming in, the output will turn on. Or if you put two ones here, the output will turn on. Otherwise, the output would be off. So if you had two 32-bit numbers, and you put every pair of bits on here, if the two 32 bits numbers matched exactly, you would have 32 wires coming out that all turned on, if they were a perfect match. Or you could do it for you could use as many of these as you need to take two registers of numbers and see if the numbers match exactly. Then take all the outputs and run them all into one big AND gate. And if that final wire turns on, that means the two sets of bits matched exactly. So if we had a piece of hardware like that, we can do comparisons. So a collection of those XOR gates is sometimes called a comparator. I think comparator is a word in the English language, but in computer science it's come up with that word. So here's an example of where we would have our page table in hardware. So let's say, for example, you have, in this case, the red wire means 1 and the black wires mean 0. So here we have a bit set to 0 and a bit set to 0. And then our page table has here, we have virtual page 00 is located at real address 0101. And virtual page 210 is located at real address 1001, which is page 9. So this is a version of our page table. So really what we're doing in this picture is we're doing something like, we're doing a small version of this. We have the virtual pages and where they are located in real memory. But we're going to do the search in hardware. So here we're basically saying virtual page 0, using 2 bits for the virtual page number and 4 bits for the real page number. Of course, a real operating system would have probably 32 bits for both on a 32-bit machine. So at this point, I'm putting a page number here, and I'm asking, is page 00, virtual page 00, is it in memory? And if so, where is it located in real memory? So I'm comparing 00 to 00, putting these two zeros into here and these two zeros into here. This wire and this wire will go through an XOR. This wire and this wire will go through an XOR. The two outputs will get ANDed together, and the line will turn on it as a perfect match. And the same thing here. If this 0 exactly matches this 1, which it won't, and this 0 exactly matches this 0, which it will, you AND the two together and this wire will be turned on. So, in this case, because 00 matched 00, then these 4 bits, 0101, will come through these AND gates, which this comparator turned on. And therefore, the 0101 will come down here at the bottom, 0101. Since these two bits, 0, 0, did not exactly match these two bits, 1 and 0, this wire was turned off, meaning it didn't match exactly. Since it didn't match exactly, this real page 91001 did not come through this OR gate. So since we found a perfect match, the real page number showed up right here. So here's an example where we can use a piece of hardware. Sometimes they call this a translation look-aside buffer. So we could put a virtual page number here, and it can simultaneously check a small subset of bits for a perfect match. And if it finds a perfect match, the set of bits that are right after it, right next to it, get copied to the final location. So then, just maybe like just looking at this picture, what would happen, or what would it mean if we put a virtual page number here, and this came out all zeros? What would you conclude could have happened? If this came out all zeros, maybe one of two things could have happened. What do you think it would mean if we put a virtual page number here? So what do? We're putting a virtual page number here, and we're simultaneously comparing it to this virtual page, and we could have more of these. So if we have no matches, what would happen? All the outputs of the comparators would all be zeros, which means all of these would be zeros. Everything going into the OR gates would all be zeros. So if we found no match, this would be all zeros. Is there another explanation for why that might be all zeros? Is there another way, maybe we found a page and it happened to be at location 0? Right, so this could have come out all zeros because we found the page and it happens to be located in frame 0. But operating systems usually, starting at page 0 is the operating system. So, or we can, what I'm basically saying is we need to know if the virtual page we're looking for is actually not in memory. We have to turn some wire on that then makes us go out to the disk drive and bring the page in. So some operating systems just make the assumption if all zeros come out here, it means the page wasn't found. You have to go out to the disk drive to get it. But what we could also do is take all the outputs of all the comparators, run them into one big massive AND gate, no, one big massive OR gate, and if the output of that is 0, that means no page was found. So if that wire turns off, we would know nothing was found. And therefore, we'd have to go out to the disk drive. We'd have to call our page replacement algorithm to go out to the disk drive, pick the page we want, and then find a place to put it. But it would be much better if we had hardware, much faster, if we had hardware doing this step. This step. The step where you take these bits, you go to your go down your virtual column looking for a match. When you find a match, you say, okay, here's where the real page is. Take these bits, copy them here, and then take the offset into the page, copy them here, and now we've built our real address. If this translation could be done in hardware, it would be done much faster. And again, we want to try to do this translation as infrequently as possible. So if we have 2 consecutive instructions, and we just compare the higher bits, the page they're from, if you compare the 2 and they perfectly match, you don't have to do a lookup. So just take, every time you run 2 instructions, take the previous instructions and the current one, run them through a comparator. If they perfectly match, no lookup needed. So we want to do this as infrequently as possible, because it'll save time. Okay. Okay. Then the other thing is, it would be nice if, when the operating system gives us page frames to put pages in, it would be nice if we could intentionally put them consecutively. Because then we can start grouping pages together, and then if page 2 is immediately followed by page 3, I'm now like going from 0 is at the bottom and I'm working my way up. If we could intentionally load page 1, 2, 3 consecutively next to each other, then it's like we can treat the whole group as one big massive page. So it'd be nice if we could do that. So So suppose we had, some storage, the first page or two is dedicated to the operating system, so hopefully these are big pages. And then process A comes in and we put them in, so then processes start showing up over time. Process A gets put into, it's a 2-frame process, so we put the whole process in. Process B has 3 frames. So we put those in right after A. Then process C comes in, which only needs 1 frame. Then 2 finishes. So now these 3 frames are finished. Now all of a sudden a new process comes in. So this is our storage. It's kind of like time is going this way. So process D comes in and only needs 1 frame. And the question is, where would you put it? If you're trying to keep storage contiguous, sometimes it's going to turn out we don't have it contiguous and our page tables will just be pointing to pages all over the place. But if we wanted to keep storage contiguous, where would you put this new incoming process D? And your 2 choices are you can put it into one of these 3 slots or one of these 4 consecutive slots. And which one would you put it in and why? And in operating systems, there's really never a right answer. There's just ways of thinking about it. Whatever happens in the future will determine if you did it, if you made a good choice. But if you had 3 free frames here and 4 here, and you're trying to keep consecutive storage, contiguous storage blocks together for future incoming programs, if you had a new program, process D, coming in, would you put it in one of these 3 frames, or would you put it one where we have 4 together? Or does it not matter, or what would your thinking be about where we should put it?
I put it in one of the 3, and then if you get a 4-frame process, you still have room.
Right, so really the 2 choices, I kind of have it written out here, the 2 choices. We could put it here. Well, we wouldn't want to put it in the middle.
Yeah.
Well, you would want to.
No, I'm saying you would want to put either 6 or 4.
Right, so really what the choice is going to do, it's going to leave a 2-frame opening and a 4-frame opening if we put it here. Or if we put it here, we're going to have 2 3-frame openings. So if I told you the next 2 programs coming, one is going to be size 2, one's going to be size 4, then the answer would be put it here. If I said the next 2 coming are going to be both size 3, then you put it here. But if you don't know what's coming, it's there is no right answer to this. So yeah, when later on in the semester we'll talk about how Linux does this. They kind of have an interesting way of addressing this question. But yeah, again, there is no right answer. The right answer would be, give me a few more minutes and let me see what comes, and I'll know what the right answer is. So, but just one other thing to take into account. So the 3 main algorithms for where you would put them is sometimes called the best fit. The best fit is the one that finds the opening that's big enough to handle what's coming, but is as small as all the ones that could handle it. So pick the smallest one of all the ones that could handle it. The worst fit is pick the biggest opening. And between the best fit and the worst fit, the 2 extreme cases, one of them leaves very small remaining blocks and very big remaining blocks. So that could accommodate various sizes of programs coming in. Finding the worst fit one leaves a lot of medium-sized blocks, which could have an advantage to it. But if we were to do either one, the worst fit or the best fit, how would we, as the operating system, figure out what would you keep track of? Like at this point, when your storage looks like this, you have 3 open frames and 4 open frames. And now all of a sudden you say, I have a program of size 1 frame. What would you look through? Would you have a data structure? Would you have a list of what's in use and what's not in use? Would you have like a vector that says page 0, 1, 2, and 3 are in use, 4, 5, and 6 are not in use? But you have to also know how big, how many frames in a row there are. So would you keep a list of what is in use? Or would you keep a list of what is free? Like, would you have a linked list that says I have 3 frees followed by 4 free ones? Or and then you'd have to search that linked list, finding the smallest one that can fit this process, or the biggest one that can fit this process, and how much time would you want to dedicate to it. So, yeah, like I say, maybe one of the reasons I want to study Linux later, Linux and Windows later on in the course, is to see how they tackle these issues, and how they maintain it. But you'd have to keep something that have to say, like, I have one block of size 3 and one block of size 4, some data structure, and you'd have to go through them. If you wanted to do best fit or worst fit, you would have to check them all. Right? The best fit says, check every free block we have and take the one that is smallest yet can fit the incoming program. The worst fit says, check all the blocks we have and take the biggest one. Well, this one you might be able to keep a data structure like a heap, something that keeps the largest, can return the largest value as quickly as possible. The other one, which kind of seems like a lazy algorithm, is just go through your empty storage until you find the first one it can fit in and just throw it in there. That might not be the best one to pick, but you can calculate this one very quickly. So if the operating system's trying to save time, that could be a good one too. If you can convince yourself best fit and worst fit are really not one is that much better than the other, and they're both taking up a lot of time, you might just say, just throw it in the first place it fits. Okay. Okay, and then the last topic is, now that we've decided to use virtual memory, your program gets copied into main memory because we've decided to cut up the memory into page blocks. The operating system decided to cut it up into page blocks. And therefore, we have to use some memory to keep track of where the pages are. We'd like to figure out how much overhead or how much storage of main memory are we using that doesn't have your program in it, but it has information about your program, or space of main memory that is being lost. I like that the definition on Wikipedia says that fragmentation is wasted space. It's not wasted, like the table that says where your pages are, that's not wasted space. We need that space. But we're taking up space in main memory just to use virtual memory, the concept of virtual memory. So we'd like to minimize the amount of the amount of main memory we use to implement virtual addressing. We'd like to try to minimize. So if picking a page size, picking it like, let's try to pick the best possible page size to minimize the amount of space we waste, I guess is the word they're using. So as you can imagine, what would be an argument for not using really small pages? If we use really small pages, what bad thing happens? Like use 1K, if your program was 2 gig and you use 1K pages, you're moving blocks in and out of 1K, what would be like the downside of having, a page size that's too small?
You have to switch between pages.
Yeah, so we'll be going out to the disk drive a lot, plus our tables would be very, very large. Well, if the operating system only gave us a couple of frames and the pages were real small, we'll be constantly going after the disk drive. But if we had very small pages and therefore the operating system gave us a lot of page frames, our tables would be very large. And we're considering that fragmentation and considering that wasted space. So this would be like if we had really small page size, and this is the amount of wasted space there. So if we had a very small page size, we're going to have a lot of wasted space. What if we had a very large page size? Suppose like the page size was 1 gig, and many programs are only 2, 3, 4K long, but it got moved in blocks of 1 gig. Then there would be a lot of wasted space at the end of the last page. Many programs would actually only be 1 page long, and there'd be a lot of wasted space at the end of the page. So if you have really big pages, you're going to have a lot of wasted space. But somewhere in the middle is going to be an optimal page size that minimizes the amount of fragmentation. So So computation of, trying to figure out what is the best page size for an operating system to use, if we had, segments, segment size, and then within the page, we're trying to pick the best page size, so the page size, P would be a variable. E would be the number of entries in your table, and F, capital F, would be the total fragmentation, the total amount of space you used up just to implement virtual memory. So the total amount of fragmentation would be the number of page entries times the entry size, plus the expected waste on the end of the last page. Take that whole wasted space and divide it by the size of the segment. So we end up having an equation F equals, and ends up being E over P plus P over 2S. And then in calculus, you can take a function, set its derivative to 0, and you get the relative maximum and minimums. And then setting it to 0 in this case, we would look for the relative minimum, and come to the conclusion that the best page size is plus or minus square root 2 times the size of the segment. So like, for example, if the segment was 128K, and we were using 1K page size, and no, 1K is 1024, then the best page size would be 512. The other thing is, if this computation ever came out to a number that wasn't a perfect power of 2, you should move it to the closest perfect power of 2, because it's always faster for translation if your page size is a perfect power of 2. So in a case like this, maybe 0.5% of the storage needed to run your program was spent implementing virtual memory. So that wouldn't be too big. Other page sizes could make this go up a lot higher. So, okay.